So today we are going to study about auto transformer starting of three phase induction motor. Previously हमें डिस्कस करथिले कि गोटे थ्री फेज इंडक्शन मोटर को केमती स्टार्ट करबा डायरेक्टली देन हमें पढिथिले रिएक्टर स्टार्टिंग मेथड एबे हमें देखिबा ऑटो ट्रांसफॉर्मर गोटे को यूज करिकि हमें केमती गोटे थ्री फेज इंडक्शन मोटर को स्टार्ट करबा हला। तो एठी हमें देखो आर वाई बी this is three phase supply, yes or no? So that three phase supply is given to a auto transformer. This is a star connected auto transformer. Okay, this is a three phase auto transformer. So B is given to a auto transformer like this. Then what we are doing, we are taking the points from the auto transformer, this point and this point. These points are taken and these points are connected to the starter winding of my three phase induction motor. This is the starter of a three phase induction motor. Which connection? Star connection. Star connection. Good. So auto transformer, the supply is directly given to auto transformer. Then from the auto transformer we are taking that supply and given to the three phase star connected starter winding. Everyone understood? Then this is the voltage V1. This is the neutral point of the auto transformer. Okay. Between R and neutral, the voltage is V1. Okay. So what is the voltage across R and Y? This must be √3 times V1, because we know that in star connection the phase voltage and line voltage is related by a factor of √3. Yes. So if this voltage is V1, this voltage should be √3 into V1, and that is my line to line supply voltage. Then this is my V1 voltage. Now tell me, this is a variable point and this is a neutral point. What is the voltage between this variable point and neutral? It is x times V1. I have already told you in the reactor starting method. Okay. So from neutral to this variable point, the voltage is xV1, and this voltage xV1 is actually given as the voltage to the winding of my starter. Okay, so starter winding is not getting V1 voltage; it is getting actually x into V1, where x is a value ranging between 0 to 1. It may be 0.1, 0.2, 0.3, or 0.4. Its value range between 0 to 1, x value. Okay, so if this pointer is in the middle, then what is the value of x? 0.5. That 0.5 is multiplied with the V1. That voltage is appeared after this winding. Okay, so this is my x V1. Okay, this is my squirrel cage rotor. Okay, squirrel cage rotor. Now, can I draw the equivalent circuit of this three phase induction motor? This is the equivalent circuit, everyone know. R1 X1 is the resistance and leakage reactance of the starter winding. X2 dash and R2 dash by S, these are the resistance and reactance of the rotor. Okay, and these are referred to the starter. The resistance and reactance of the rotor is referred to the starter. And you all know that if we are considering the starting case, then slip is always equal to 1. Good. So slip is 1. So the resistance is R2 dash by S. Okay. So now tell me, if slip is 1, the resistance of rotor is reduced or high? It is minimum or high? High. So you are saying that if S is equal to 1, the resistance is high. No. I have already told you, when slip becomes 0.1 or 0.2, that 0.1, 0.2, when you divide the value R2 dash by S, that value is going to increase. Like suppose R2 dash is 10 and you are dividing S value 0.3. This is equal to 10 divided by 3 by 10, 100 by 3, which is equal to nearly 33. So if S value is 0.1, 0.2, 0.3, then the overall resistance is more. If S value is 1, the overall resistance is less. S is equal to 1, the resistance is basically 10. But if S value is 0.3, the overall resistance of this resistor is 33. That means at standstill condition, sleep is 1, that means the rotor resistance is minimum. Everyone understood? If rotor resistance is minimum, then tell me, maximum current is going to flow. Okay, so that huge amount of current is going to flow through the windings. Okay, so that's why we are introducing auto transformer method, so that the voltage which is the winding is getting is reduced. Okay, so the voltage which is the winding is getting is XV1. Everyone understood? So now tell me, in this circuit, what is ZSC? ZSC is the total impedance of this circuit. Okay, total impedance means R1 plus R2 dash plus X1 plus X2 dash, and the voltage you are applying to this circuit is XV1, because my winding is getting XV1. So this circuit is getting the voltage XV1. Okay, so the voltage is XV1 and the impedance of this circuit is ZSC. So if you divide voltage to impedance, you will get the current. So that is the starting current, and the formula is XV1 divided by ZSC. Everyone understood? Now, I have told you what is ISC. ISC is nothing but V1 divided by ZSC. So if rated voltage is applied to the winding, rated voltage, not XV1. When V1 is applied, then that rated voltage divided by ZSC will give you ISC. Okay, so in place of V1 divided by ZSC, I can write what? ISC. So the starting current is simply X time ISC. This relation everyone understood or not? So the starting current in this case is X time ISC, where ISC is equal to V1 divided by ZSC. Now, from MMF balancing of auto transformer, there is an auto transformer. What is MMF balancing? Listen, I have written over here the turns ratio is 1:x. That means this winding behaves as primary as well as secondary. In an auto transformer, the same winding will act as a primary winding and secondary winding. So this one is my primary and this much is my secondary. Okay. So if this is the amount of turns at 1, then this amount of turns is X. If one number of turns is there in the primary, X number of turns is there in the secondary. So based on that, if V1 is the voltage in the primary, what is the voltage in the secondary you are getting? XV1. Understood? So what is MMF balancing? MMF balancing is saying that the flux is constant. Okay, because that is a single core. Okay, so that's why the flux is constant. Flux constant means MMF must be equal. So what is the primary MMF? Primary MMF is current into number of turns. MMF is always what? Current into number of turns. So what is the current flowing in the primary winding? It is written over here, supply circuit. Okay, and the number of turns in the primary is, how much turns are there? One number of turns. If I assume one number of turns is there in the primary, then X number of turns should be there in the secondary. So MMF balancing is saying the amount of MMF in the primary should be equal to MMF in the secondary. How to calculate MMF? Primary MMF, current into number of turns. So what is the current flowing in the primary winding? It is supply current. And what is the number of turns in the primary? 1. So that's why I have written over here 1 into supply current. Current into number of turns. That should be equal to secondary MMF. And secondary MMF is secondary current into secondary number of turns. So secondary number of turns. What is the secondary number? It is X. And what is the current in the secondary side? X into IS. So that's why what I am writing over here, X is the number of turns in the secondary and the current in the secondary side. Current in the secondary side is basically X into IS. So X into IS. Now this product will give you IS. I supply is equal to X square into ISC. Everyone understood how this relation I have arrived? Okay. Then this formula you have already know that the starting torque to full load torque is equal to starting current to full load current square into slip at full load divided by slip at starting. And you know that slip at starting is 1, so I can replace ST by 1. And what is the starting current? Starting current is X time ISC. So I can replace starting current by X into ISC divided by full load current whole square. So that X square goes out and it is ISC by IFL whole square into SFL. This is the ratio of starting torque to full load torque in case of a auto transformer starting. Okay. Then you know that if I want to write the ratio of starting torque with auto transformer starting, I am taking the ratio. Starting torque in case of auto transformer starting to my reference is what? Direct online starting is my reference. So I am comparing with the reference one, that is direct online starting. What is the amount of torque, starting torque in case of auto transformer starting divided by what is the amount of torque with direct online starting. And you know that starting torque directly proportional to square of the applied voltage. Yes. So what is the amount of voltage you are getting in the auto transformer starting? How much voltage you are getting? XV1. So that XV1 voltage square. Okay, XV1 voltage square. And what is the starting? What is the voltage you are giving in the case of direct online starting? That is V1 voltage. In dual starting, directly V1 voltage you are applied to the far-fetched circuit or not? Here I have written V1. In the previous lectures video, you can see that in a dual starting the applied voltage in this circuit is V1, but here the applied voltage is XV1. So I can say that the starting torque is always proportional to square of the applied voltage. So in that sense, I can write that the torque, starting torque due to auto transformer starting is equal to XV1 whole square, the applied voltage whole square. And in case of dual starting, the applied voltage is V1 whole square. So this relation is also holds true. So here V1 square cancel out, only thing left is X square. So from this you can say that starting torque with auto transformer starting is equal to X square times starting torque with DOL starting. Everyone understood? That is the relation of starting torque between the two methods. Okay, the X square is the relation factor. Okay, which relate the starting torque in auto transformer starting and starting torque with the dual starting. The ratio is always equal to X square. Everyone understood? So why I am writing over here X into ISC? Because my starting current is XV1 by ZSC is equal to X into ISC, and that starting current is actually flowing in which winding? Starter winding. So that's this is my starter winding, and the current to flow in the starter winding should be the starting current, which is X into ISC. So here I can also write like this: I starting is equal to X time ISC. Understood? But this supply current, what is the relation of this supply current with this starting current? That I have established in this way. By balancing the MMF, I have established the relation. Supply current is X square times ISC. Everyone understood? Or I can say that supply current is X time starting current. Because this X into ISC is starting current, so supply current is X time starting current. So now tell me, which current is greater current and which one is a lesser current? Supply current is more or the starting current is more?
Supply current.
Supply current is more. Yes. Everyone? Yes. Sure. What do you think? The relation is supply current is equal to X square into ISC. Yes or no? Supply current is X square into ISC. That is supply current is equal to X into ISC. This X into ISC is nothing but your X into ISC is your starting current. So supply current is basically equal to X into starting current. Understood? So let us assume starting current is 10 ampere and this X value, just guess 1, 0.2, 0.3 like this value. So you guess a value between 0 to 1. 0.5. So supply current is how much? 0.5 into 10. That is 5 ampere. So supply current is 5 ampere and starting current is 10 ampere. Understood? That means your supply current is less as compared to starting current. Everyone understood? So how this is possible? Listen. This is the current. Okay. There is another current flowing in this way. So this current and this current adds and it is flow as starting current. So that's why starting current is more as compared to supply current. Understood? There is a, you can apply KCL over here. There is a current like this. There is a current coming in this way, and these two current adds up to give you this current. Understood? So this is the auto transformer method of starting. So what you have understood from this method of starting, your supply current gets scaled by a factor of x square. Supply current is scaled by a factor of x square. Okay, and your starter current gets scaled by a factor of x. Starter current means starting current. Okay, the starting current is your starter current and which is scaled by a factor of x. And the supply current is also reduced by a factor of x square. Starter current, your supply current is reduced by a factor, so it means your motor is safe now because your supply current or starting current is reduced. Okay, your current flowing in the starter is also reduced by a factor of x. This is our objective, to reduce the current flowing in the winding of the motor. Okay, so in this method of starting, you reduce the supply current by a factor of x square, you reduce the current flowing in the winding by a factor of x, and the torque ratio gives you x square. If you compare the starting torque of auto transformer with dual starting, you will get a